guys, so in this demo I'll show my supervised deep learning pipeline that detects the diabetic retinopathy grade 0 to 4 and macular edema risk 0 1 from the fundus images using ResNet 18 with transfer learning. So I use Kaggle dataset. Each split train validation test has an images folder and annotation.csv with the image name, retinopathy grade and risk of macular edema. This makes it directly for usable for our supervised classification. So if I say why I have used this ResNet 18 and why, it is a compact CNN with the skip connections that helps to gradient to flow in deeper network. So I chose it because it fast, stable and accurate with the ImageNet pre-training, which is so perfect for medical images where dataset is limited. I add two heads, a 5 class head for DR grade and a binary head for edema risk. So if I show you the pre-processing part, in this I resize images to the 38384 and convert to float and normalize with ImageNet mean STD. For training, I used light augmentations, mole rotations, flips, and mild affine transformations to improve the generalization. I also handle imbalance with class weights for grades and post weight for edema. Optionally, there is label smoothing for overconfidence. So this is the whole training setup. In this, all the training configurations are predefined. So end to end with Adam W, cosine learning rate schedule and early stopping on a validation macro F1 and AMP when available. So the multitask loss is cross entropy for grade plus BC with the logis for edema. So as the results and visualizations, I have generated the learning curves, ROC edemas, bar charts, and the confusion matrices. So here are the learning curves: grade accuracy, climbs and stabilizers, edema IOC approaches 0.98. The final numbers, if I show you, this is the last grid that I have gained for the outputs. So 0.6696, you can see overall results in this, and as a confusion matrix there, uh, this is the confusion matrix from the training I have gained. So the uh, most errors between adjacent grades typical in DR, but it can be reduced in the optimizations techniques by in the future.
Hi, I'm Ramandu. This is my FirstNet B0 model for retina disease. It's predict the DR grade 0 to 4 and macular edema risk from the single fundus images. Now let's get into the data and pre-processing techniques. Our dataset is split into train, validation test, images are center, crop resized and fed as a 380 to 380, then resize inside the model 224 to 224 to match the FirstNet B0. Models and labels come from the CVS. Train is balanced to handle the class Q. After nutshell, this is implemented model efficient net B0 pre-trained on image net as a shared backbone. After global average pooling, we branch into two heads of 5 ways of max for DR rate and 6.4 edema. We regularize the dropouts and light L2 regularization techniques. Training is to stay first heads only, then we unfreeze 60 to 100% of the backbone with the lower LR. So all the discussed useful parameters and all the configuration are defined in this YAML files. So as the default batch sizes I have set into 32. Also epoch stage 1 and 2 sequence to 5 and 10. Also for unfreeze ratio I pointed to zero point 0.6 also. And so I have generated the full evaluation package AUC, ROC, curves, training, validation, learning curves, confusion matrix, and classification reports showing 65% validation accuracy for DI grading and strong edema performance. Also, training curves, validate lines are smooth with a small gap, stable learning, mid or fitting and strong edema. So, training confusion matrix most prediction are correct with errors mainly between the adjacent grades. Also, the validation ROC edema base curves well above the diagonal with a UC approximately 0.95. Good is a good discrimination on validations, and also the test ROC edema based even higher AUC approximately 0.97 strong generalized to the held out test sets. That's the overall idea of.
In this demo, I will walk through my supervised deep learning project that detects library retinopathy and grade 0 to 4 from the retinal fundus images. For this project, I used the retinal disease detection dataset from Kaggle. It contains thousands of retinal images analyzed by different disease stages. I divided the dataset into training, validation, and testing splits so a model could learn from one set, tune its performance on another, and finally get the evaluated on unseen images. Now, if I explain why I chose the convenience tiny model, it because the convenience tiny is the modern and efficient CNN architecture that performs really well on the image classification task. It's basically an upgrades version of ResNet redesigned with the ideas from the vision transformers. It uses the layer normalization, depth-wise convolution, GLU activation, which helps it extract more meaningful features and converge faster with fewer parameters. Before I train in, I did some image pre-processing, resize all the images into 224 into 224, normalize them using the ImageNet statistic, and applied simple augmentation like random horizontal cliff improve generalization because the dataset was slightly imbalanced. I used the weighted random sampler to give each class a fair chance during the training. The model was trained into two phases. First, I trained into the classification head with the black-bone frozen, and then I fine-tuned the entire model for about the 37 epochs. During training, both training and validation accuracy increased steadily while loss curves kept decreasing, which means the model was learning effectively without overfitting. So I will show the overview of the training. This is the loss accuracy and the balance and the learning rates. And I will show the confusion matrix. This is the confusion matrix. So in the end, the model achieved around 6%, 60% validation accuracy, and the macro F1 score above zero point 0.5. So overall, the convenience tiny model gave the strong and balanced performance for retina disease detection, proving that it's great fit medical image analysis. Thank you.
Hi, I am Pradiksha, and in this project, I implemented a deep learning model using DenseT 1-to-1 for retinal disease detection. The goal is to automatically classify fundus images into different stages of diabetic retinopathy. I used a real-world dataset from the Kaggle, which contains around 200 and 300 retinal images divided into training, validation, and test sets. I choose DenseT 1-to-1 because it connects every layer with all the previous ones. This helps the network reuse features, train faster, and avoid losing important information. The model has several dense blocks and the transition layers that pass information efficiently through the network. Before training, all images were resized, normalized to help the model learning better. I used focal loss to handle imbalance between classes and AdamW optimizer to adjust weights and during the training. In my code, train.py handles the full training loop. It tracks accuracy, loss, and F1 score after each approaches. The best model is automatically saved when it gets the higher validation F1. Then I use evaluate class to test the model and create the reports and the confusion matrix. Finally, the plot matrix, plot compare eval generates all the result graph using showing accuracy loss and F1 score trends. I trained 3 models with image sizes 224, 320, and 448 pixels. The 448 pixel model gave the best performance with the 67.5 high accuracy and the macro of 0.57. The graph shows that both accuracy and the F1 steadily improved uh, with higher image resolution. This confusion matrix shows how well my model predicted each disease classes. The darker diagonal means the correct predictions. For example, the darker diagonal means correct predictions. For example, it correctly detected 82% of healthy eyes. Most mistakes happen between nearby disease levels, like mild and moderate. Overall, DenseNet 1-to-1 worked really well for the retinal disease detection. With more data and better argumentation, the accuracy can go even higher. Thank you.